Right, good afternoon, everyone. So we will continue with our tutorial today. So previously, just to recap, we have already completed last week tutorial. We have already completed tutorial for chapter 4. But if you miss out or you still need certain guidance, I already uploaded the video on your VLE. So you may refer to the tutorial video if you need help for tutorial chapter 4. Then subsequently, last week, I have also already entered chapter 5. If you remember, chapter 5 is the chapter related to collection and analysis of rate data, or basically meaning chapter 5 is all about when you have experimental data, of which we will use the experimental data depending on the different method to identify the two important information, okay, which is first is the rate law. Basically means we want to find the reaction order of the reactant in the reaction, because once you know the reaction order, you can already determine the rate law. And second, we would like to also find out the value of K. So you remember, I taught you two methods already, half-life method as well as integral method. Okay, so half-life method and integral method, if I'm not mistaken. Differential method, salah terbalik. Differential method and half-life method. Okay, so meaning kalau half-life method, okay, we have to conduct this set of experiment, of which we have to then get the data. We have to change the data into the data for y-axis, x-axis. Then we plot the graph. On the graph, we will identify from the slope and the y-intercept, which we'll use to determine the reaction order and the reaction rate constant. So as simple as that. Okay, but the challenge is that you have to first understand what kind of plot that you will get. So the pro of the information here is that you don't have to plot the graph. As I told you previously, the graph will be given to you. So means you don't have to plot the graph manually. The information on the graph also will be given to you. Okay, just that the challenge for you is to interpret the data, okay, correlate with the correct equation, and then to find that two important information, reaction rate constant and also the reaction order, and then use that to solve the problem subsequently. Okay, so later lecture 3:30, I will continue with one more method. Okay, sebab we haven't finished at the chapter 5, we have two more methods, sorry. Just that from that two method, one method we will learn in detail, another method is just general one. Okay, so today tutorial will cover the two method lah. Will cover the question related to the two method that we have already learned. Then later on during lecture 3:30 tu, the third method I will continue terus dengan soalan tutorial untuk cover that particular method terus. Right? Okay. So the first question, if you want to look at the questions are already in VLE under tutorial chapter 5 if you want to refer to it. Right. So the question says, the gas phase reaction of pure A is shown below. So the first information yang penting, this is a gas phase reaction and this is using pure A. So means initially 100% mole of A is inside the reactor for the reaction. The experimental runs were performed, kejap saya buka besar sikit. The experimental run were performed in an isothermal, isobaric, constant volume batch reactor with 10 kilojoule activation energy. So by now you dah tahulah. If we talk about activation energy, that will be our EA. So kalau ada EA, definitely later on you will need to use Arrhenius equation. In some ways, the Arrhenius equation we will use to solve certain problem later on. Then they say from the plot given here, so the plot you see the y-axis is ln T half, the x-axis is ln CA naught. Okay, so saya dah last Thursday I taught you. If you see the plot ada T half tu, you definitely tahu itu adalah half-life method because T half is half-life. Okay, hanya half-life method of which you will see your graph, you will have T half punya value. Or in this case, dia adalah ln T half. Okay, sebab kamu kena ingat chapter 5 ada method yang berlainan. Method berlainan tu ada graph yang berlainan. So first of all, you kena identify lah daripada plot tu terus method apa. Sebab method method yang you choose will be the method that you will use the equation for your calculation. So from this plot, dia kata the gradient was determined as negative 0.64. So your slope, your gradient M is negative 0.64 and your y-axis intercept as 1.75. Okay, so dia bagi juga your y-axis intercept 1.75. Sekejap Right, so y-axis dia 1.75. Okay, so that's all the information that is given to us. And then now let's go to the question. Okay, so the question first is, determine the reaction order and the specific reaction rate constant. Okay, so soalan dia kata, tentukan reaction order, your alpha. So the reaction order refers to reaction order with respect to reactant A lah. Sebab hanya ada satu reactant saja, which is reactant A. Right? And then the specific reaction rate constant. So they want us to find K. So find alpha, find K. So essentially, dia nak kita tahu dulu, find first your rate law. Okay, so the first step is of course to first know which method. Sebab method berlainan ada equation yang berlainan. So I told you, as the plot is T half, then definitely lah dia punya method will be half-life method. So if you look at half-life method, you go check the equation. So the equation is provided to you, so you don't have to memorize. But you have to then understand the what is the equation is all about. So the equation is given as ln T half, which represents your y-axis, equals to 1 minus alpha ln CA naught. So your ln CA naught is your x. Hence, 1 minus alpha will be equal to your gradient. Okay. And of course, the back part, plus ln 2 power alpha minus 1 per k alpha minus 1. So the back part that I'm highlighting right now, this is essentially your C ataupun your y-intercept. Because then only we can express the equation as y equals to mx plus c. Okay, so now you find the correlation with the equation and the graph. So that's the challenge. Kamu kena faham correlation between plot yang kamu ada dengan equation yang juga kamu ada. So means if you want to find alpha is from the gradient. So the gradient 1 minus alpha itu will equal to your gradient which is negative 0.64. Okay, so you can see the step 1 minus alpha equals to your gradient which is negative 0.64. So you will get your alpha as 1.64 if you calculate correctly. And as I told you before, you run up to the nearest integer. Okay, so the nearest integer will be 2. Okay, so means your alpha is 2, or we can say that your reaction is second order with respect to A. Okay, so sebab dalam kes ni hanya satu reactant sahaja, reactant A. So the reaction order will refers to your reactant A. So when you know the reaction order, you can already write down your rate law. So rate law dia akan menjadi minus RA equals to K CA power of 2. Sebab reaction dia second order with respect to A. So essentially tu yang kamu kena tahu, correlation antara plot dengan equation. The gradient tu bersamaan dengan nilai apa dalam your calculation in your equation. And from there, you can elucidate the rate law. So done. So next part, kita nak cari K, kita dah cari alpha, kita dah tahu rate law. Next is to find K. So as we have already deduced, your y-intercept equals to this entire equation lah. Ln 2 power alpha minus 1 per k alpha minus 1. So this entire thing equals to your y-intercept, which is 1.75. Okay, so you can replace the alpha value. So you may wonder, like I explained the lecture, shall I replace the alpha with 1.64 ke ataupun 2 selepas round out? You use either one also, I will not give you, I will give you the marks, okay? But to be more accurate, technically, you use the value of alpha before your round up untuk mencari nilai K from the equation, right? Okay. So if you replace correctly, okay, this is a little bit tricky sebab kamu kena tengok kamu ada ln di sebelah kanan. So kamu kena tahu kalau saya nak hilangkan ln di sebelah kanan, what I need to do untuk hilangkan ln tu, kotak kamu tak boleh dapat nilai K. Okay, but if you calculate correctly, You will get your value K as 0.1516. Okay, so next part, which I explained last Thursday, is on the K unit. So K unit too is you have to you have to deduce yourself from what I taught you before in chapter 2, where the unit of K is determined by the reaction order. Kalau dia adalah zero order, the unit of K is concentration per time. Kalau first order, the unit of K will be per time. If second order, the unit for K will be 1 per concentration time. Sebab tu kamu tengok sini unit dia jadi liter per mole minute. Sebab dia kan 1 per concentration time. So kalau 1 per concentration, mole per liter, 1 per mole per liter jadi liter per mole times with the minute at the bottom. So that's how you get the unit liter per mole minute for the unit of K. Okay, so that's for the, sorry. That's for the first question. So the first question is not that difficult technically, just that kamu kena tahu equation. So katakan kalau kamu tengok equation yang salah, confirm lah part A ni dah salah. So kalau part A dah salah, part yang seterusnya semua akan salah juga. Sebab if you deduce the wrong rate law, you deduce the wrong value of K, then the soalan-soalan semua pun akan salah lah juga. Sebab base kita punya design equation kan based on rate law, based on the value of K. Right. So we go to the second question. So you must understand, soalan chapter 5, dia akan correlate balik dengan soalan dalam chapter 1, chapter 2, chapter 3, chapter 4. So maybe in the beginning you find it's easy sebab yelah, kalau dah ada graph, dah ada nilai, macam soalan A tu senang kan? Tetapi you must understand that information become the basis for the next question that will be from other chapter. Okay, so let's say we go to the question number 2, B. When the reaction in run 2 was repeated at a new temperature of 50 Celsius, it took 18 minutes longer to achieve the same conversion of 80%. Determine the original temperature of the experimental run. Okay, so kamu tengok soalan ni, memang soalan ni I purposely do it a bit confusing so that you understand how the questions can be. Okay, so dia kata soalan ni, dia repeat balik run 2. Okay, so kita tengok kat dalam graph, this is your run 2. So imagine kalau kamu lupa, half-life method adalah, as I taught you, kita ada series of experiment. Okay, run pertama akan menggunakan CA0 yang, katakan CA0 pada 2 molar. Okay, I put in the reactor, saya catat masa, berapa masa diperlukan untuk 2 molar ni menjadi 1 molar. Half of its initial concentration. Lepas tu saya take out, I start back with fresh solution. Let's say I prepare 1 molar pula, saya tentukan berapa masa diperlukan untuk mencapai 0.5 molar. So I have different runs sebab each run menggunakan CA0 yang baru. Okay, so dia kata, run kedua ni, kalau kamu perasan, ln CA0 dia 0.8. Okay, so by right, kalau kamu dah tahu ln CA0 tu 0.8, kamu dah boleh dapat CA0 dia. So you know, dia akan menggunakan CA0 yang apa untuk run yang kedua, and dia repeat run kedua ni pada suhu yang baru, which is 50 Celsius. If you notice, from the original run, kita tak tahu temperature dia. Kalau kamu perasan dalam soalan, dia tak beritahu pun. Masa kita nak run initially the reaction, original run tu, dia tak beritahu kita suhu berapa. Sebab tu, nilai K yang kita dapat ni, technically we do not know at what temperature. Okay, so you assume now we do not know the temperature, but I know the value of K. So, or you can say, this is at K1. Kita tahu K1, kita tak tahu T1. Okay, that's the easiest way to say. I have K1, I do not know T1, and I now have T2. So, temperature yang kedua, 50 Celsius. So, this is a confusing part. Tahu nilai K1, tak tahu temperature 1. Tahu temperature 2 pula sekarang, which is 50 Celsius. And dia kata, it took 18 minute longer. Dia mengambil masa 18 minit lebih lama to achieve the same conversion of 80%. So you remember soalan tadi kata we run in a batch reactor. So bila saya run pada suhu baru 50 Celsius, masa tindak balas saya menjadi 18 minit lebih panjang. So maksudnya katakan originally pada suhu T1 yang saya tak tahu tu, it takes me 20 minit to achieve 80%. Now kalau saya run pada 50 Celsius, dia akan mengambil masa 20 plus 18, 38 minit untuk mencapai conversion yang sama. Okay, so kamu remember, right? Apa yang akan berubah apabila kita ubah suhu, mestilah nilai K, right? You remember I told you kenapa why reaction time changes, okay, when reaction takes place is one of bila suhu berubah is because of your the change of the value of K. Sebab tu bila nilai K berubah, definitely pengiraan kamu pun berubah, nombor kamu dah berubah. Okay, and kamu pun ingat saya pernah beritahu kamu, when you increase temperature, reaction time become shorter. So dalam kes ni dia kata tindak balas menjadi lebih panjang. So kamu boleh deduce suhu tindak balas kamu ni sebenarnya diturunkan sebab tu mengambil masa yang lebih panjang. So means your original temperature should be below 50 should be above 50 Celsius. Sorry. Maknanya masa asal kamu ni suhu asal tindak balas kamu should be more than 50 Celsius. Sebab tu bila dikurangkan kepada 50 Celsius, masa tindak balas menjadi lebih panjang. Okay, so that's our deducement. But we haven't really solved the question yet. So dia kata, determine the original temperature of the experimental run. So dia nak tahu kita punya nilai T1. Okay, kita ada nilai K1 which is 0.1516 pada suhu T1 yang saya tak tahu. I got K1, I don't have T1. I have T2. So saya ada T2 pula. Okay, so apa masalah dia bila kita nak solve ni? So you remember kalau menggunakan Arrhenius equation yang ni, okay, I go to the down first. This red, the one that I highlighted. Kalau kamu ingat, kita ada kan Arrhenius equation yang ada kombinasi K1, T1, K2, T2. Tapi kombinasi tu mengatakan for the equation, kan saya ada 4 unknown, right? I have to know 3 unknown, baru saya boleh solve unknown yang keempat. Kamu kena faham, bila kita ada satu equation, okay, kalau kamu nak solve dia, kesemua unknown tu kena tahu dahulu kecuali that one unknown that you want to solve. So if we want to use this equation, what is the problem? Okay, K1 kita tahu, which is the one that you get from part A. Suhu asal punya K1 kita tahu. Suhu T1 ni yang kita nak cari. Okay, so let's say I bold the T1. T1 kita nak cari. T2 kita tahu 50 Celsius. I already know my T2 is 50 Celsius. So by right, I should know my K2. Saya kena solve dahulu K2. Kalau saya tak boleh solve K2, saya takkan dapat T1 daripada persamaan Arrhenius ini. Maksudnya, saya harus tahu K2 pada 50 Celsius ataupun berapa nilai K pada 50 Celsius. Okay, baru saya boleh dapat temperature asal saya sebab saya dah tahu K pada asal temperature saya. So that's the challenge. Macam mana nak dapat dulu K pada K2 ataupun K pada suhu 50 Celsius. That's why they give you this information. Dia kata ambil masa 18 minit lebih panjang untuk mencapai conversion yang sama. Maksudnya, kalau saya boleh tahu the original reaction time at my initial temperature, at my experimental temperature, kalau saya tahu masa tu, I add 18 minit kepada masa original tu, saya boleh dapat nilai K2 saya. Okay, so that's the correlation. Saya kena tahu dulu masa tindak balas saya pada suhu asal yang saya nak tahu. Saya tambah 18 minit kepada suhu, 18 minit kepada masa tindak balas tu, I will use that reaction time to find my new K ataupun my K2. Okay, so how do I do this? Explanation this sounds a bit complex, right? Okay, so we do it one by one. Right, so first of all, okay, EA, okay, kita kumpul dulu what information that we have. I have my EA, 10 kilojoule per mole. So we write it down as 10,000 joule per mole. I know my T2 is 50 Celsius. Suhu baru saya 50 Celsius. Saya tahu X saya, kes suhu asal, suhu baru ke suhu lama masih conversion sama 80% as mentioned in the question. I know my T2, masa tindak balas pada suhu yang baru sama dengan masa tindak balas pada suhu asal plus 18 minute. Okay, then saya pun tahu K1 0.1516 from part A, and saya tahu rate law dia minus RA equals to KCA power of 2. Okay, so next, how to solve this? Okay, so now you have to remember when we talk about reaction time dalam batch reactor, kamu kena check balik chapter 4. Okay, kamu ingat kalau batch reactor, we will always find reaction time. Okay, and you remember dia ada equation yang berlainan bergantung kepada rate law yang berlainan. So if you check, if you have rate law minus RA equals to KCA power of 2, fasa dia tak apa sebab liquid atau gas equation masih sama. And batch reactor, equationnya diberi sebagai reaction time equals to 1 per K Ca0 in bracket X per 1 minus X. Okay, ini adalah contoh di mana soalan chapter 5, but you still have to come back and look at chapter 4 punya design equation. So this equation is given to you. So what can we do with this equation adalah, saya cari dulu masa tindak balas saya pada suhu yang lama. Okay, so that means I find first reaction time at my old temperature. Kalau kamu get confused, T kecil tu means time, T besar means temperature. Okay, because sometimes I put in symbol, I scared you got confused. T kecil refers to reaction time, tau refer to residence time, T besar refers to temperature. So this T1 ni refers to reaction time lah pada suhu asal. So 1 per K1. So K1 tadi yang kita dapat daripada part A, K pada suhu asal. CA0. So CA0 ni pun kita kena tahu macam nak cari. Okay, so how do we find it? Kan dia dah kata the reaction is in run 2. So kamu tengok plot, run 2. Okay, kalau kamu tengok nilai paksi X dia adalah 0.8. This 0.8 refers to ln CA0. Ln initial concentration of A pada run kedua sama dengan 0.8. But you want to find CA0, right? So you have to know lah kalau ln CA0 sama dengan 0.8. So CA0 equals to exponential 0.8. Okay, so you have to find yourself time to calculate by yourself. Okay, but you will get the CA0 as 2.2255 mole per liter. So that's your CA0. You can replace your CA0 inside. So kamu kena ingat, dia repeat run yang sama. Dia just ubah suhu. So maknanya CA0 pada suhu asal, CA0 pada suhu baru masih CA0 yang sama, which is 2.2255. So done. So then in bracket, you find your X is 0.8. Okay, so when I calculate this, okay, as I'm highlighting in the question, you will get the time at the original temperature as 11.8559. Maksudnya bila saya run eksperimen saya pada suhu asal yang saya tak tahu ni, masa tindak balas dia adalah 11.8559 minit. Okay, first step. Step kedua, sekarang saya kena cari masa tindak balas yang pada suhu baru. So masa tindak balas pada suhu yang baru, saya tambahlah 18 minit kepada 11.8559. So now I get my T2, masa tindak balas pada suhu baru. So dia menjadi 29 minit 0.8559. So kita akan guna balik equation yang sama, tetapi sekarang kita nak buat apa? Kita nak cari K pada suhu baru. So, dia punya step tu a bit confusing lah kan? Step pertama, tahu dulu masa tindak balas suhu asal. Lepas tu tambah 18 minit, dah dapat masa pada suhu tindak balas baru. Dah tahu masa tu, kita guna equation yang sama untuk mencari pula nilai K pada suhu baru. Okay, so it will get your time at your new temperature, 29.8559. Okay, equationnya masih sama, equation merah ni Okay, sama dengan 1 per K. So sekarang adalah K pada suhu baru. Times CA0 masih sama. As I told you, new reaction, new temperature, old temperature, the CA0 was the same from the run 2. And in bracket, 0.8 divided by 1 minus 0.8, you will get the new K at the new temperature as 0.0602. So remember now, tadi saya kata masalah kita untuk solve problem ni, kita tahu K1, kita tak tahu T1. Kita nak cari T1, right? Saya dah tahu saya tahu K1, saya tahu T tu, suhu baru tu saya tahu, tapi saya tak tahu tadi nilai K pada suhu baru ni. So when I solve the equation, 2 kali equation tu, now I get my K at the new temperature. So saya dah boleh solve lah. Saya dah ada 3 daripada 4 unknown yang saya nak solve. Now I can use the Arrhenius equation as I shown you right now to find the new temperature. Just beware, equation ni kamu pun dah biasa guna. Just beware, when we talk about the temperature, it was in Celsius, but you know, when I use Arrhenius, due to the reason the value of R, the unit will be in Kelvin. Then your temperature, you must change from Celsius to Kelvin by adding 273.15. So you can see here equation dia, K2 0.0602, K1 0.1516, K2 adalah pada suhu baru, 0.1516 adalah pada suhu yang lama. Okay, EA 10,000 joule per mole divided by R 8.3144. In bracket, T1 ni kita nak cari. So T1 tu kita biarkan. T2 kita dah tahu. Suhu baru kita adalah 50 Celsius. Tukar kepada Kelvin. You solve this, you eventually get your new temperature as 429.80. So remember if I told you, suhu asal tu mesti lebih tinggi daripada suhu baru. Sebab masa tindak balas tu jadi lebih panjang bila kita masa tindak balas menjadi panjang apabila dia adalah 50 Celsius. Maksudnya suhu asal tu lebih tinggi lah. Sebab tu masa tindak balas menjadi lebih panjang apabila kita sejukkan kepada suhu yang lebih rendah. So 50 Celsius, if I convert to Kelvin, is 323.15. That was the new temperature, but my original temperature was actually 429.80, which is much higher. So sometimes when you do calculation, you can use it to deduce sama ada calculation kamu tu logik atau tidak. So macam tadi saya beritahu kamu, by right, nilai suhu asal tu kan lebih tinggi disebabkan ni. So when you calculate, you can verify betul tak apa yang kamu assume dengan nilai yang kamu kira. Right, so done with question B. I do admit question B is a bit confusing. Okay, so just that I want to train you from the very beginning how you actually solve different types of questions. Okay, from the equation that you have, the interpretation of the information that you have. So let's go to the second, number C, part C. The initial concentration used in run C is now used in a single CSTR with 40% conversion. Determine the space velocity of the reactor. Okay, so dia kata sekarang, expander run kamu dulu tu kamu run dalam batch reactor, right? Okay, dia kata sekarang kita nak run dalam CSTR. Tapi kita akan menggunakan initial concentration daripada run 6 yang tadi kamu run originally. So kamu check balik graph. Okay, run 6, the ln CA0 is 2.8. Okay, so kita tahu sekarang kalau ln CA0 sama dengan 2.8, hence CA0 will be equals to exponential 2.8. So saya dah tahu dah initial concentration untuk run 6 saya. Dan saya nak guna concentration ni untuk dalam CSTR dengan conversion 40%. I want to find space velocity of the reactor. So you have to come back, check balik pula chapter 4 untuk untuk CSTR. Kalau ni adalah case CSTR, gas phase, actually in this question, this is a gas phase reaction with the rate law minus RA equals to KCA power of 2. So if you have these three combination, rate law, minus RA sama dengan KCA power of 2, CSTR, gas phase, apa dia punya design equation. So kalau you check, by right, the design equation will be the one that I'm highlighting in the red color, which is volume CSTR equals to FA0 X in bracket 1 plus epsilon X, tutup bracket, power of 2 divided by KCA0 square in bracket 1 minus X, tutup bracket, power of 2. Okay, so again, this equation rate is the one that will be given to you during the exam. Okay, dalam test pun equation ni diberi. Okay, so if you wonder kenapa tak ada yang part P naught per P, T per T naught, sebab dah soalan tadi dah kata isothermal, isobaric. So part yang pressure tu dah tak ada, part yang temperature tu pun dah tak ada dalam equation kita because the question says isothermal, isobaric. Okay, so done. Okay, tapi kita nak cari space velocity. So kalau kamu ingat, space velocity formula dia, we learn in chapter 2, space velocity adalah 1 per space time. Kalau space time, kalau space time, dia volume per initial volumetric flow rate, V per epsilon naught. Kalau space velocity, terbaliklah, space velocity sama dengan epsilon naught per V CSTR. So sekarang you have to tweak your equation in order for you to find the space velocity. So kalau kamu tengok yang part soalan yang font merah tu punya formula, kita tak ada epsilon naught. Tapi kita tahu nak cari space velocity, we have to have epsilon naught. Baru kita boleh gantikan atau tukar dalam bentuk yang menjadi space velocity. Okay, but we also know, which I taught you, if I have one FA naught at the top and one CA naught at the bottom, I can divide it. Satu FA naught bahagi dengan satu CA naught di bawah, I will get my epsilon naught. So sekarang saya dah perkenalkan epsilon naught dalam equation saya. So it become epsilon naught X in bracket 1 plus epsilon X power 2 below K sekarang menjadi hanya CA naught sebab satu CA naught tu saya dah bahagi dengan FA naught, right? So become 1 CA naught at the bottom, 1 minus X power of 2. So now I already have my equation di mana I can find the volume and I have the epsilon naught. Okay, so tapi belum settle lagi kan sebab kita nak cari space velocity. So remember back, space velocity akan sama dengan epsilon naught per volume CSTR. So then what happens to my equation? So kamu imagine epsilon naught ni saya tinggalkan di sebelah kanan. Okay. Volume CSTR ni saya pindah daripada kiri ke kanan. Selebih tadi yang kat kanan tu kena bawa ke kiri. So maksudnya yang pembawah tadi K CA naught in bracket 1 minus X power of 2. Kalau dia pindah ke kiri dia akan menjadi pengatas. Dan X in bracket 1 plus epsilon X power of 2 di sebelah kanan dia adalah pengatas. Bila kita pindah ke kiri dia jadi pembawah. So now you have already derived your own equation to find the space velocity. Okay, so this is a challenge of reaction engineering. Equation tu diberi, okay, just I told you, I give you the rate equation. Kamu pun dah faham konsep kalau saya bahagi FA naught dengan CA naught, saya dapat satu epsilon naught. Kamu pun faham konsep apa tu space time, apa tu space velocity. So you have to be able to derive equation tu sendiri berdasarkan information yang kamu tahu. Okay, now that kita dah derive equation dia, so we can solve it. But you have to know sama ada information tu cukup atau tidak untuk kita solve. So we go one by one, right? So first K. So we know the value of K. The K originally was 0.1516 from part A. Dia tak kata suhu berubah kan? Kalau dia tak kata suhu berubah, you can use the K yang originally kamu kira pada part A. Sebab part C tak kata apa-apa pasal perubahan suhu. Maksudnya K yang kamu kira waktu asal tu kamu boleh terus gunakan nilai K tu 0.1516. Dan what about CA naught? So tadi dia kata CA naught was in run 6. So from the graph, run 6, ln CA naught sama dengan 2.8. Okay, so if ln CA naught sama dengan 2.8, CA naught equals to exponential 2.8. So you get your CA naught 16.4446. So CA naught settle. X was 0.4, so ganti X. Kat bahagian bawah, X again 0.4. And one more is epsilon. So kita kena cari epsilon. Jangan ada beza epsilon volumetric flow rate. Epsilon adalah untuk mencari dalam equation ni lah. Okay, so epsilon kalau kamu ingat, formula dia adalah YA naught sigma. Equation ni diberi. Okay. YA naught, just now question says pure A. So YA naught is 1, 100 more % of A initially. So YA naught is 1. Sigma, okay, sigma punya equation tak diberi because nilai sigma will change, right? What is nilai sigma? If you forget, is the ratio of your stoichiometric coefficient of which it is positive for product, negative for reactant. If you remember, the reaction is 1A produce 2B. Sebab tu dia punya formula untuk mencari sigma equals to B per A, positive for B because B is a product. So B per A minus 1 or technically is minus A per A. So A tu reactant, right? That's why nilai dia kena minus. So you will get your B per A is 2 per 1 sebab 1A menghasilkan 2B. So you will get your epsilon as 1. Okay, so you replace epsilon with 1, you replace your x again, so you solve this entire equation, you will get your space velocity for your CSTR as 1.1447. Okay, so that's done for question number 1 for half-life method. So you can see here, just to recap back, okay, half-life method tu sebenarnya adalah normally it will be the first part of the question sebab daripada graph tu kamu tahu rate law dia, kamu tahu nilai Q. Soalan yang selanjutnya adalah soalan daripada chapter 4, chapter 3 di mana kamu akan apply rate law yang kamu cari, nilai Q yang kamu cari itu kamu akan apply untuk mencari benda-benda yang lain dalam soalan tu. Okay, so that's the part that you really have to understand how the questions are correlated with one another. Okay, so done. Question number 1, we will go to second question. So today tutorial will not be a long one sebab kita ada 2 soalan. Satu method saya hanya bagi 1 soalan saja. Okay, sebab yang soalan permulaan tu senang je. So means kamu faham equation, kamu dah boleh correlate dengan plot. Tapi soalan-soalan yang lain tu bergantunglah chapter-chapter yang saya dah pernah ajar. So kamu kena faham kalau kamu belajar chapter 5, kamu tak boleh belajar in silo ataupun belajar chapter 5 tak kisah chapter lain pun tak boleh sebab dia akan berkait soalan dengan chapter-chapter lain. Right, so I go to the next question. Okay, the gas phase decomposition of A to produce B and C is given below. Okay, so the gas phase reaction, 1A menghasilkan 1B dan 2C. The mixture initially consists of 60 mole % reactant A and the remaining compound I and inert in the reaction. So dalam reaction ni, asalnya walaupun it's only reactant A, tapi dia bukan 100% A. Dia ada juga inert dalam kamu punya initial mixture. Ataupun I can say, my YA0 is 0.6. So you cannot always assume kalau reactant tu A, YA0 tu 1. Tak semestinya, kecuali kalau dia kata pure A. Unless they say pure A, then you have to find out berapa sebenarnya YA0. Kalau dia cakap pure A, baru kamu boleh assume YA0 is 1. Okay, so dia kata, to perform the reactor scale up, it's vital to determine the reaction rate data. The reaction is carried out in a constant volume batch reactor at 700 Kelvin. Okay, so soalan ni beritahu temperature kita. Temperature reaction kita 700 Kelvin. Activation energy 4 kilocalorie per mole. So saya tahu EA 4,000 calorie per mole. Saya tahu temperature saya 700 Kelvin. The concentration time data is used to plot a graph of ln minus dCA per dt as a function of ln CA. So tengok sekarang graf kita dah berpaksikan benda yang lain. Tadi ln T half, ln CA0. Sekarang dia adalah ln minus dCA per dt and ln CA. So automatic dah bukan method half-life lah. Kalau tak ada data T half, bukan dah half-life method. Okay. So dia kata gradient was determined as 0.65, kecurunan kamu 0.65, y-intercept kamu negative 1.65, and this says the unit of concentration mole per dm cube and time is in minutes. So dia beri kita unit kepekatan, unit masa. Dia beritahu kita intercept, y-intercept, and they give us the gradient as well. So let's look to the question number 1. Determine reaction order and frequency factor of the reaction. So this is a bit different, right? Tadi soalan pertama dia suruh cari reaction order. Sama, tapi dia suruh cari K. Soalan ni dia suruh kita cari reaction order and dia suruh kita cari frequency factor. So kalau kamu lupa, frequency factor tu datang daripada Arrhenius equation. The frequency factor stands for the A. In your Arrhenius kan, dia sama dengan K equals to A exponential minus EA per RT. So this A is the one that they want to find, the frequency factor. Tapi sebenarnya sama je lah. In order nak cari A, kena dah tahu K dulu kan. So almost the same like previous question. I use the graph to find the reaction order and thus the rate law and also to find K. Okay, so again, the first step. To determine first, method apa? So you have to check. Kalau your plot is ln minus dCA per dt melawan ln CA, there's only one equation and one method that you will plot this graph, which is differential method. So kalau kamu ingat last Thursday saya berhempas pulas ajar kamu kan macam mana kamu nak kira untuk plot graph tu. So kamu bayangkan dalam soalan kamu tak payah pun dah bimbang ataupun you don't have to headache yourself. Remember I taught you ada equation initial point lah, interior point lah, final point lah, kena ln kan lah, kena negative kan lah, so on and so forth. So when I taught you, I teach you how to plot the graph. Tapi dalam question, I don't expect you to calculate to plot the graph. Memang graph tu dah diberi. Maksudnya nilai ln minus dCA per dt tu dah diberi kepada kamu. So the graph also dah diberi. But you can see, like the previous question, when certain information is given to you, you are to use it to solve even harder part of the question sebenarnya, right? Okay, so technically, the method is what we call as differential method. Okay, so you check equation dia. So equation dia given as, you don't have to memorize the equation. List of equations, dalam list of equation yang saya bagi dalam test atau exam, I don't tell you which method to which equation. So kamu kena tahu sendirilah kalau equation ni method apa. Okay, so differential method equation says that ln minus dCA per dt. So this is your y-axis, the same as your graph, equals to alpha ln CA. Ln CA is your x-axis as shown in the graph. Therefore, alpha is your gradient. Betul tak? Y equals to mx, right? So, alpha is your gradient plus ln K. So, ln K is your y-intercept ataupun your C. So, you get y equals to mx plus C. So, from that, kamu dah boleh correlate. Your gradient sama dengan alpha, your reaction order. Your ln K equals to your y-intercept. Okay, so we do one by one. So order of the reaction, alpha equals to gradient equals to 0.65. From the question, this is the gradient is 0.65. Okay, given here 0.65. Therefore, alpha equals to 1. Kita round up lah daripada 0.65. We round up to the nearest integer. Integer tu angka bulat. You will get 1. So meaning your reaction is first order with respect to A sebab you only have one reactant. So the reaction is first order with respect to A. Therefore, your rate law minus RA equals to KCA. And since saya dah tahu suhu dia pada 700 tidak balas saya, so I put it as K700. So saya tahu that K yang saya kira nanti atau yang saya akan guna nanti adalah pada suhu 700. Okay, done. Next part. Okay. Walaupun dia tak suruh cari K, tapi kamu ingat kan nak cari frequency factor from Arrhenius equation tu, saya still kena tahu K. So from the equation, ln K equals to your y-intercept. Okay, your graph given, the y-intercept value is negative 1.65. Okay, so kamu tahu lah kan, kalau ln K sama dengan negative 1.65, K sama dengan exponential negative 1.65. So you get your K value as 0.1920. And because this is a first order reaction, the unit of your K will be per time. And tadi dalam soalan katakan unit untuk time adalah minit. That's why nilai K kamu akan menjadi 0.1920 per minute. Okay, so then Baru kamu cari kamu punya frequency factor from the equation, Arrhenius equation. K equals to A exponential minus EA per RT. So, saya dah tahu K, saya dah tahu EA, saya dah tahu R, saya tahu temperature saya 700 Kelvin. I can then solve to find my A, 3.4061. So, this question is a bit indirect. Okay, sebab yang sebelum ni saya ajar kamu, saya asyik beritahu kamu cari alpha, cari K. Tapi soalan ni dia lain sikit. Dia suruh cari alpha, part yang sama. Tapi yang lainnya, instead of suruh cari K, dia suruh kamu cari A. Tapi kamu mesti kena faham benda yang sama. In order to find A, indirectly saya kena cari K. Tanpa ada nilai K, I can never get the value of A. So sometimes that's the part that you have to understand. What you have and what you don't have yet in order to solve the problem. Right, okay, so the last part for today, sebab question nombor 3 ni saya belum ajar method dia. Nanti saya akan ajar 3.5 kemudian. So masa saya ajar lecture tu, saya terus sambung dengan soalan tutorial nombor 3. So the last question for today, okay. The same reaction, so bila masa kamu nampak ayat same reaction, meaning suhu tindak balas tu sama. Nilai K tu kamu boleh guna nilai K yang sama. So that's why sometimes kamu nak kena faham ayat tu. Bila you understand the sentence, you understand what value the same, what value will change. Whenever they say tak ada perubahan suhu, apa nilai K yang kamu tahu tu kamu guna je. Kamu dah tak payah bimbang nak cari nilai K yang baru. Okay, dia kata conducted in a 10 dm cube plug flow reactor. Reaction sama ni sekarang saya jalankan dalam PFR dengan volume dia 10 dm cube. Okay, so kamu kena ingat, bila saya run eksperimen yang nak plot graf ni, saya akan guna batch reactor. Saya dah ajar kamu kan, bila kita nak run, kita nak tentukan rate law, tentukan nilai K, this experiment we run dalam batch. Tapi information yang kita dapat lepas tu, rate law dia, nilai K tu, kita akan guna untuk kita design reactor yang berlainan. So you have to understand that concept as well. Means nilai K takkan berubah, rate law pun takkan berubah bila kamu tukar reaktor. Sebab tu kamu kena faham, rate law, value K adalah terikat kepada tindak balas. Kamu run pada reaktor berlainan pun, rate law dan nilai K masih sama. Even nilai EA pun masih sama. Just that, dalam konsep, dalam case nilai K, kalau kamu ubah suhu, then nilai K itu akan berubah. Okay, tapi kamu tukar reaktor, all that value will not change sebab dia terikat kepada tindak balas. As long as you run the same reaction, you will still use the same value of K, the same value of your rate law. Okay, so dia kata sekarang, I run the same reaction in a 10 dm cube plug flow reactor. They want you to determine the initial volumetric flow rate with 80% conversion. So initial volumetric flow rate itu adalah epsilon naught kan? So dia sebagai kita volume, dia nak kita cari epsilon naught, dia beri kita nilai X. Okay, so this question is very easy, but again, kamu kena faham dia berkait dengan chapter 4 kembali. So, kamu kena ingat dalam chapter 4, kalau you have gas phase reaction, gas phase PFR dengan rate law dia minus RA equals to KCA, you have to find, kamu kena ingat, kalau tiga syarat ni, hanya satu equation yang akan penuhi tiga syarat ni, which is given to you in this red font color that I'm highlighting. The volume PFR equals to FA naught per KCA naught in bracket 1 plus epsilon tutup bracket ln 1 per 1 minus X minus epsilon X. So this red font equation is provided to you, but again, remember, saya akan beri kamu list untuk semua equation. Kamu kena tahu equation mana digunakan untuk case yang mana satu. Okay, so, but this equation dah betul. Part kiri dah betul memang volume. Tapi part kanan, soalan kata nak cari epsilon naught. Okay, you realize dalam part kiri tak ada epsilon naught yet. Okay, so, kita nak cari epsilon kan kalau kita ada epsilon. Okay, but again, you know how to modify the equation sebab when I have one FA naught at the top, one CA naught at the bottom, when I divide them, I will get epsilon naught at the top. FA naught bagi dengan CA naught dapat epsilon naught. Okay, part yang lain dalam equation saya masih sama. Okay, K masih sama. Yang part bracket kat belakang semua masih sama. So when I have this, barulah saya boleh solve. Okay, sebab I know my volume PFR is 10 dm cube. Belah kanan saya tahu. Belah kiri, okay, epsilon naught saya nak cari. K at 700 was the one you get from part A. Sebab suhu tak berubah, nilai K tu masih sama. So I can use the value of K the same one. Okay, let's go behind epsilon. So epsilon kena cari balik lah. So part ni kamu kena berhati-hati. Kamu kena betul-betul faham equation dia tak fix in the part of your sigma. Okay, sebab epsilon betul equation dia sama untuk mencari epsilon, which is YA naught sigma. Tapi dalam case ni YA naught dia dah bukan satu, right? Sebab part A dia kata pure A. So YA naught tu satu. Tapi part B dia kata initially 60 mole percent A and 40 mole percent inert. So asalnya YA naught dia adalah 0.6. Okay, so what I wanted to say is YA naught tu tak automatic satu kecuali kalau dia kata pure A. Kalau dia tak cakap, kamu kena tengok betul-betul berapa mole persen atau mole fraction A yang masuk pada waktu asal. Okay, so YA naught 0.6. So yang bahagian belakang ni pun juga nak mencari sigma pun formula dia tak fix because it depends on what is your reactant, what is your product. Tapi konsep dia adalah is the ratio of your stoichiometric coefficient over A, of which it must be positive for product, negative for reactant. Tadi dia punya reaction is 1A menghasilkan 1B dan 2C. That's why ia menjadi B per A plus C per A because both B and C adalah product and your A was the sole reactant. Sebab tu dia menjadi 1 per 1, B per A plus C per A, 2 over 1 minus A per A, which is 1. So you get your epsilon as 1.2. So repeat again, epsilon can be negative, can be positive, it can be any value berdasarkan pengiraan kamu. Okay, so sometimes if you get your epsilon negative, don't worry. If you calculate correctly, it may be correct, right? Okay. Once I get epsilon, I just replace inside lah. The rest saya dah ada information, conversion saya dah tahu. So you get your epsilon naught, okay, your initial volumetric flow rate as 134.41 dm cube per minute. Okay, so I think question number 2 somewhat taklah susah sangat, tapi kamu kena faham yang soalan chapter 5 ni biasanya hanya part permulaan yang kamu menggunakan plot. Soalan seterusnya akan berdasarkan soalan daripada chapter-chapter yang berlainan sebab yang important from chapter 5 sebenarnya kamu kena tahu macam mana nak dapatkan rate law, dapatkan nilai K dan soalan seterusnya adalah soalan yang daripada chapter-chapter yang berlainan. Okay, so as I told you, today tutorial is quite fast sebab kita hanya belajar 2 method. Okay, so you have 1 hour to rest and actually technically 2 hours because I will meet you back at 3:30 for your lecture for today. Alright, so if you have no question, attendance tak apa, saya ambil daripada attendance